In this video I'm going to explain the concept of vector projections, and you can see that I've written a statement there saying we can express a vector A as the sum of a vector component parallel to B and one perpendicular to B. So I'll try and express that using a diagram that might make a little bit more sense. But basically we're saying, well, any vector can be expressed as the sum of two or more other vectors. So in this case, what if I wanted to express the vector A that I've drawn there as the sum of one vector that was parallel to B and one that was perpendicular to B? So let's try and sketch those. I might try the perpendicular one first. So perpendicular to B would be something like that there, and then one that's parallel to B would be that one there. So maybe if I called those two vectors, this one here I'll call the vector U, and that one up there I'll call the vector W. So I'm saying that the vector A here could be expressed as U plus W. Now in fact we use this idea all the time when we're just using normal component form, because I and J are two vectors that are perpendicular to each other. It's not immediately obvious here why it might be useful to do what we're doing here, but like maybe the scalar product itself, over time we'll see that this in fact does have a number of uses. So let's note that I could express U as some scalar multiple of B, couldn't I? In this case it looks like a scaled down version of B, but depending on the magnitude of B it could be a scaled up version. So K is just some scalar value, some real number. And that means that I could express the vector W, which from that first statement up there, W would be A minus U, and therefore I could write it as A minus K times B. Okay, because it's A minus U. Now, using my knowledge of the scalar product, I can say that vector B times, dot vector W is going to be equal to 0, because those are perpendicular vectors, aren't they? So that's because B is perpendicular to W. So I know the dot product of two perpendicular vectors is going to be equal to 0. Alright, let's substitute in here then for W. So I said W is equivalent to A minus KB. So what do I have then? Expanding that dot product there, I've got B dot A minus, well that's going to be K B dot B is equal to 0, and I know, or I can rearrange therefore to find an expression for K. So K is going to be equal to the dot product of B and A. So I'll write that as A dot B instead of B dot A. So it's going to be A dot B divided by B dot B. Alright, so there's a few steps of working out there that you need to sort of follow along, make sure you understand those. But now if I take that expression for K and sub it right back up here, let me highlight where I'm subbing it back in. So I said U was equal to K times B. So therefore down here I can say, well, U must be equal to this value for K that I've found here. So that would be A dot B over B dot B, which, as it should be, is a scalar value, isn't it? A scalar divided by a scalar is a scalar, so that's the value of K, and U is equal to K times vector B. Okay, so again I've subbed that into the thing that I highlighted in yellow up above. U is equal to K times B, where I found that K can be written as that quotient of scalar products. Now that expression that I've got there can be called the vector projection of A on B. Okay, so look back up at the diagram again where vector U is on the diagram. that vector u is called the vector projection of A on B, or of A in the direction of B. On your formula sheet you'll see it written as vector projection of A on B. The form that it's written in there at the moment is probably the form that's easiest to calculate it in, but it's actually written a little bit differently on your formula sheet, so I'll show you how we get from that to what's written on your formula sheet. So remember that the dot product of any vector with itself, so where I've got b dot b, that can be written as the magnitude of b squared, which is magnitude of b times magnitude of b. So let's say therefore u could be written as a dot with vector b over its own magnitude. So that would be, and then times vector b over its own magnitude. Okay, so I've kind of split that magnitude of b squared into magnitude of b times magnitude of b on this line. So any vector divided by its own magnitude, remember, produces a unit vector in that direction. So that dot product could be written as a dot unit vector b, and then again vector b divided by its own magnitude is unit vector b. So that's the form that it is on your formula sheet. Now that's not quite as easy for calculation purposes, but it is actually quite useful in another way. So if we go back up to our diagram here, let me just write this under our diagram. So we're saying u is equal to a dot unit vector b times unit vector b. If you think about what that's saying that the vector u has a magnitude. Let me get my highlighter here. So this first part here is actually the magnitude of u, isn't it? Because we're saying it's that times unit vector b. So unit vector b, this second part of the expression here, unit vector b is just a unit vector, well, let me grab a pen there, unit vector in the direction of b. Okay, so it's a vector of length 1. So therefore the magnitude of u must be the thing that I've highlighted in green here, which is a dot unit vector b. So a dot unit vector b, which is the magnitude of the vector projection of A on B, is called the scalar projection of A on B. And it's kind of one of the ways that we could think about it is sort of to say it's the amount of vector A which is pointing in the direction of B. So if we sort of dropped A down in a perpendicular sense onto B, then that's the amount of A that would be in the direction of B. Alright, let's just think about the vector W. Okay, so we found an expression for vector U, so that's the vector projection of A on B. If we wanted to find the projection of A perpendicular to B, which is our vector W, well, rearranging our initial expression for A, we would just say W is equal to A minus U, so therefore we could say W is equal to A minus this seemingly sort of cumbersome expression there, or using the form that it is on the formula sheet, we could say it's just minus a dot unit vector B times unit vector B. So that would be the projection of A perpendicular to B. Now one final thing before I do a quick example is that these projections are sometimes called resolutes. Because we can talk about resolving vector A into vector u and vector w, or resolving vector A into a component parallel to and perpendicular to vector B. I'll finish this video here and then I'll do another one with an example using these.